So here we're going to use the second derivative test to help us find local extrema, just to get a little bit of practice with it. So here I have f of x equals x cubed minus 9x squared plus 24x minus 10. So I want to start by finding my first derivative. So here I have 3x squared minus 18x plus 24. I'm going to take that derivative, set it equal to 0 so that I can find my critical points. Let's see, I have a greatest common factor of 3. So that'll leave me with x squared minus 6x plus 8 is equal to 0. And then I can factor this guy. Let's see, I should have x minus 4 times x minus 2 is equal to 0. So my critical numbers are x equals 4 and x equals 2. I should also check, if I'm just looking for local extrema, I should also be looking to see, hey, where is the first derivative undefined? But if we look at the first derivative, 3x squared minus 18x plus 24, that's a polynomial. We know it exists everywhere, so we know that 4 and 2 are our only critical points. So we could continue this problem using the first derivative test. We could go and draw out our number line and say here's 2 and here's 4 and start plugging numbers in. But here we want to see how this is different than the first derivative test. We actually want to use the second derivative test. So the way I'm going to do this here is now I'm going to find the second derivative. So f double prime of x, so that should be 6x minus 18. So there's my second derivative. I'm going to take my two critical numbers and plug those into my second derivative that I just found. So f double prime of 4, this is 6 times 4 minus 18. This is 24 minus 18. Let's see, that gives me a positive 6. I would be careful to jump to any conclusions here. I always like to draw out my thought process for these problems. So, okay, we have the second derivative is positive. What does that mean? That means we have a graph which is concave upward, which means that we have a minimum. So what that means is that f of 4 is a local minimum. So that is 1, and then you could go and of course find the y value by evaluating f of 4, but I'll let you do that part. I want to do the same thing then with 2, so let's do that in black here. F double prime of 2, this is equal to 6 times 2 minus 18, and let's just make sure we don't get these mixed up. Here I have 12 minus 18 gives me negative 6. So the second derivative is negative. So okay, the second derivative is negative. That means my function must be concave downward. And what do we see right there? I see a local maximum. So this is a maximum. So that means that f of 2 is a local maximum. I think for a lot of functions, the second derivative test is actually a lot easier and faster to use than the first derivative test. But if I don't specify, if I don't say use this test, if all I said was find the local extrema, then you can use either one. You can use the first derivative test or the second derivative test. But there will be at least one question on a quiz or an exam that'll say, hey, go find the local extrema using the second derivative test. Or perhaps I'll tell you, I might say something like, I know that, and this is just a kind of an aside here, if I know that f prime of 5 is equal to 0, and f double prime of 5 is equal to negative 2, what can then we conclude about f of 5? Well, we would say, okay, second derivative, well, first of all, have a horizontal tangent line. Second derivative is negative, so we have a concave down graph. In that case, we know that f of 5, that's a local maximum. So just be sure that you practice the second derivative test, you understand what it's telling you, because I promise I will ask at least a couple questions about the second derivative test. And let's look at one more example here, something that's not a polynomial. Here I have e to the x minus 5x. Again, I need to start by finding those critical points, which means I need the derivative. So f prime of x is e to the x minus 5. I'm going to take this derivative and set it equal to 0. E to the x equals 5, and then if I solve this equation, I have to use natural log on both sides, so x equals natural log of 5. Again, I should also consider where is my first derivative undefined, but in this case, e to the x minus 5, that's defined for all real numbers, so I know that x equals natural log of 5. That is my only critical number. So I have my critical number. Now I just need to determine, is this the location of a local maximum or a local minimum? I want to use the first derivative test, or excuse me, the second derivative test, which means I need the second derivative. So, okay, I'm going to take the second derivative, f double prime of x, derivative of e to the x minus 5. That's just going to be e to the x. So I'm going to take my critical point that I found, natural log of 5, and plug that into my second derivative. So f double prime of natural log of 5. This is e to the natural log of 5 power. If I simplify this, e to the natural log of 5, that's just 5. So I know that the second derivative is a positive 5. So what does that mean? That means we have, no, that's right, a function which is concave upward, since we have a positive second derivative. And what do we have here? We have a local minimum. So that means that f of natural log of 5 is a local minimum. So I think that the second derivative test it's really pretty nice. It saves you quite a bit of time when you're working with nice functions. Now, if we're working with an ugly function that maybe you needed like multiple derivative rules to find the second derivative, in that case, I don't think that would be a good candidate to use the second derivative test for. But for polynomials, for relatively simple functions, the second derivative test can save you a little bit of time, and it'll help us in the next set of examples.